Welcome to the deep dive. Today, we're tackling harmonic regression. It's a really powerful technique for understanding those repeating seasonal patterns you see everywhere in time series data. It's stock markets, maybe, or epidemiological trends.
Absolutely. These recurring cycles, the seasonality, it's fundamental in so many areas.
Yeah, exactly.
And being able to spot it and, more importantly, model it effectively, well, that's just crucial for analyzing data that changes over time.
Right. Whether you're in business trying to predict sales dips and peaks, or in healthcare tracking disease outbreaks, or even, say, environmental science looking at ecological cycles, understanding these rhythms is, well, it's vital.
It really is. It helps you make informed decisions.
And that's exactly why we're diving into harmonic regression today. We've pulled together some interesting sources, statistical analyses, detailed methods from journals like the International Journal of Environmental Research and Public Health, even some software documentation.
Good stuff.
Our goal really is to give you a solid handle on this technique, show you its power for analysis.
And it's quite elegant, actually. At its heart, harmonic regression uses those fundamental sine and cosine waves, the basic oscillations we see all through mathematics, to break down these sometimes complex-looking seasonal patterns.
Yeah, it helps sort of dissect them into predictable bits.
Exactly, into understandable components.
Okay, so let's start right at the core then. What's the basic mathematical model look like?
Okay, so the fundamental harmonic regression model, we usually write it as ZT equals cos 2 pot plus a plus set.
Whoa, okay. Let's unpack that a bit. ZT, that's just the data point at time t.
Correct. The value of your series at a specific time, t, then that's your baseline level. Think of it as the average. The data is fluctuating around.
So like for monthly shop sales would be this sort of average sales figure if there were no seasonal peaks or troughs.
Precisely, yeah. Then you've got duce gamma, that's the amplitude.
Amplitude, how big the swing is.
Exactly. The intensity of the seasonal variation, how high the peaks are, how low the troughs are relative to that baseline.
Okay.
Then omega, that's the frequency of the oscillation. This is directly linked to the period of a season. So for monthly data with an annual cycle is 1/12. One cycle per 12 months.
Right, because the cycle repeats every 12 time units. Makes sense.
Then T is just our time index, and phi, that's the phase angle.
Phase angle, what does that control?
That determines the timing. It pinpoints when the peak occurs within that cycle. It essentially shifts the cosine wave left or right along the time axis.
Okay, so it lines up the mathematical wave with the actual peak in the data.
Exactly. And finally, epsilon t, that's just the error term. It's the bit of the data that our nice smooth wave model doesn't perfectly capture.
Yeah.
The noise, essentially.
Right, the random variation or factors not included. So this model gives us a smooth, regular wave. But the source has mentioned another way to write it, one that's better for actually doing the calculations.
Yes. For estimation, for actually fitting the model to data, it's often more convenient to rewrite it using both sine and cosine, like this. Zit t equals 1 plus zitessen to pot plus zitsikos plus is sec.
Okay, so now we have a vitesse and a mixie instead of the gamma and phi.
Exactly. Zititas and ditsi are the coefficients we estimate using standard regression techniques. They neatly combine the information about the amplitude and the phase angle from the first form.
How do they relate back?
Well, you can calculate the amplitude arc as the square root of vitesse squared plus ditsc squared, and the phase angle is related to the arctangent of bettest divided by bettest.
I see. And the benefit is?
The big benefit is that this second form is linear in terms of the parameters we need to estimate, bettest and bettess. That means we can use standard, well-understood linear regression methods to find their values, which is much easier computationally than directly estimating bits of fit in the first non-linear form.
Ah, okay. That is much more practical, isn't it? You estimate the betas using standard tools, and then you can just calculate the amplitude and phase if you need them. Very neat.
It is. It simplifies the fitting process considerably.
Now, you mentioned O is 112 for monthly data with an annual cycle.
Yeah.
How does that change for, say, quarterly or daily data?
Good question. The principle's the same. For quarterly data with an annual cycle, there are 4 quarters in the cycle, so O would be 14.
One cycle every 4 quarters. Yep.
For weekly data, it gets a little messier because a year isn't exactly 52 weeks. It's about 52.25 widths. So O is roughly 1 divided by 52.25.
Okay.
And for daily data, again, accounting for leap years, the average year is about 365.25 days. So O would be approximately 1 divided by 365.25 for an annual pattern.
So the key is always 1 over the number of time units in one full seasonal cycle.
Precisely. It defines how quickly the sine and cosine functions complete a full oscillation relative to your time unit.
Okay, that clarifies the frequency part. Now, real-world data often isn't just oscillating around a flat average, is it? You often see trends that things generally increasing or decreasing over time. Can harmonic regression handle that too?
Oh, absolutely. That's one of its strengths. You can easily extend the basic model to include trend components.
How'd that look?
Well, imagine you have monthly data, like before, with that annual seasonality, but you also see a steady increase over several years. A common way to model that would be something like ZT plus BCC cos 2 tie 12 plus BC 2 tie 12 plus V year A plus VT.
Well, let's break that one down. Theory is still the baseline, but maybe the baseline at the very start.
Yeah, the intercept term, effectively the baseline at time 0.
Then the sine and cosine terms are the same as before, capturing the monthly wiggles within each year. Here, T means the month within year E.
That's right, indexing the month.
And the new part is B year E. So I's is the year number, like year 1, year 2, year 3.
Correct, the year index.
And B year is the coefficient telling us how much the baseline level changes each year, the slope of the trend.
Exactly. It quantifies the magnitude and direction of that linear trend over the years. So this model lets you estimate both the repeating seasonal pattern and the overall upward or downward drift simultaneously.
That's really useful. And the sources also mentioned adapting this for different kinds of data, like counts.
Yes, the framework is flexible. If your data isn't normally distributed, say you're counting events like disease cases, which often follow a Poisson distribution, you can embed this harmonic structure within a generalized linear model, or GLM.
Using something like a log-link function.
Typically, yes. A log-link is common for Poisson regression. The core idea of using sine and cosine terms to model the seasonality remains the same, but you fit it within the appropriate statistical framework for your data type.
So you can disentangle seasonality and trend for various types of data. That's quite powerful, but
Yeah.
there was a limitation mentioned. The basic sine and cosine wave is symmetrical, right? Smooth up, smooth down.
That's a very important point. Yes, the standard harmonic model assumes a symmetric seasonal pattern.
What happens when that's not realistic? I'm thinking like maybe flu season cases. They shoot up fast, maybe trail off slower.
Exactly the kind of scenario. Real-world seasonality isn't always symmetrical. Flu seasons, certain retail peaks, maybe agricultural cycles, they can have sharp, rapid increases to a peak, followed by a more gradual decline, or vice versa. A standard harmonic regression might struggle to capture the shape and, critically, the exact height and timing of those sharp peaks accurately. It tends to smooth them out.
So how do we get around that? How can we adapt the model for these spikier patterns?
Researchers have come up with some clever ways. A common strategy involves a two-step procedure.
Okay, step 1.
Step 1 is usually to fit a basic harmonic regression model, maybe just the first harmonic sine and cosine pair, primarily to get an initial estimate of the timing of the seasonal peak. Let's call this estimated peak time theta.
So first, find roughly when the peak usually happens.
Got it.
Step 2.
Step 2 involves fitting an extended model. This model uses modified sine and cosine functions transformations of the basic ones. These transformations are specifically designed to create an asymmetrical shape around that estimated peak timeout.
How do they do that?
They often incorporate terms that behave a bit like a quadratic function near the peak, allowing for a sharper rise or fall. They might use time variables shifted relative to a, or functions that change behavior depending on whether you're before or after the estimated peak time.
So it kind of warps the standard wave shape to match the data better.
That's a good way to think about it.
Yeah.
Models C and D mentioned in some of the research papers are examples of these extended forms. They use specific mathematical transformations involving Dord and time-shifted variables to mimic that sharp peak and allow the amplitude to vary more realistically around the peak season.
So you can tailor the wave shape, in a sense. It's impressive how you can build that complexity onto the basic sine cosine foundation.
It really is. It shows the flexibility of the approach.
And the research you looked at used these techniques on real data, right? Can you give us a couple of examples?
Yes, the papers had some great illustrations. One looked at hospitalizations for salmonella infections among older adults in the U.S. from 91 to 2002.
Okay, what did they find?
The harmonic regression clearly picked out the annual seasonal pattern, more cases in the warmer summer months, peaking consistently. Being able to quantify that peak's timing and strength helps public health folks maybe targeting food safety messages more effectively then.
Makes sense. What else?
Another study examined lab-confirmed cases of Shigella, another bacterial infection, in India over a decade, 2003 to 2013.
And there.
There, the analysis showed two key things. First, a strong seasonal peak around June, which they linked to the monsoon season potentially affecting water quality. Second, and very importantly, it revealed a significant increasing trend in the number of cases over that decade.
Ah, so it caught both the cycle and the overall rise.
Exactly. That combination is crucial for understanding the changing disease burden and planning interventions. You see the yearly rhythm, but also the bigger picture trend.
And wasn't there one on pneumonia and influenza deaths, too?
Yes, in the US from 1968 to 1978. That analysis, unsurprisingly, showed a clear winter peak, typically January, for P&I deaths, flu season essentially. But interestingly, the model also detected a decreasing trend in those mortality rates over that period.
Oh, why would that be?
Likely reflecting improvements in healthcare, maybe vaccine development or uptake over those years. So again, it's separating that known seasonal spike from a longer-term change in the baseline level.
And did those modified models for sharp peaks help in these examples?
Yes, particularly for the infectious disease examples like Salmonella and Shigella, the papers reported that the extended models, the ones using that two-step approach and modified functions, provided a statistically better fit. They were better able to capture the magnitude and the sometimes rapid upswing in cases leading to the peak compared to just the basic harmonic model.
These real-world cases really highlight the practical value, don't they? It's not just abstract math. It gives actionable insight.
Absolutely.
Now, looking beyond these core ideas, the outline mentions some more advanced stuff, like using multiple harmonics. What's that about?
Right. Sometimes the seasonality isn't just one simple annual wave. You might have other cycles happening at the same time, maybe within the year or even within a month or week.
Like a 6-month cycle on top of the annual one, or weekly patterns in daily data.
Exactly. Think about daily retail sales data. You'd expect an annual pattern, sure, but also a very strong weekly pattern weekends versus weekdays. To capture these more complex situations, you can add more pairs of sine and cosine terms to the model, each pair tuned to a different frequency.
So you'd have your annual terms, 1365.25, and weekly terms, 17.
Precisely. You might even include harmonics for semi-annual patterns, OCU 2365.25, or other relevant frequencies. It's like layering different wave patterns on top of each other to match the data's complexity. This allows for a much richer description of the time dynamics.
Okay, that makes sense for capturing more intricate cycles. What about the level of detail in the data itself? Does using, say, weekly versus monthly data change things?
Oh, definitely. The temporal aggregation level matters quite a bit. Using higher resolution data daily or weekly instead of monthly can potentially reveal finer details in the seasonal pattern.
Like sharper peaks, or maybe cycles you wouldn't even see in monthly totals.
Exactly. You might get more precise estimates of peak timing and shape. However, more data means potentially more noise, and the models can become more complex to fit and interpret. So there's often a trade-off. Weekly disease data might show outbreak dynamics much more clearly than aggregated monthly counts, but it's also more data points to handle.
Right, a balance between detail and practicality. And beyond the model structure and data frequency, what else should analysts bear in mind?
Well, several things. It's really important to think about potential confounding factors. Are there other variables changing over time that could be influencing the trend or even the seasonal pattern you're seeing?
Like policy changes or demographic shifts, or maybe weather patterns that aren't perfectly seasonal.
Precisely. Exploring specific exposure variables that might drive the seasonality, like temperature for ice cream sales or school terms for certain infections, can add a lot of explanatory power. And a big one, statistically, is autocorrelation.
Where data points close together in time tend to be more similar than points far apart.
Exactly. Time series data is often autocorrelated. Failing to account for that can mess up your statistical inference, your p-values, your confidence intervals. There are standard techniques within time series analysis to address autocorrelation, often by modeling the structure of the residuals, the 8 term.
So need to check those model assumptions carefully. The outline also hinted at some quite advanced tools, things like MVGAM or BOISA and R-tensor product smooths. How do they fit in?
Yeah, those represent the cutting edge, building on these harmonic ideas but adding a lot more flexibility. Packages like MVGAM, for example, are powerful because they can model seasonal effects that aren't fixed but can actually change smoothly over time.
So the seasonal pattern itself might evolve from year to year.
Exactly. Maybe the peak gets earlier or the amplitude changes. MVGAM often uses techniques like tensor product smooths, perhaps with cyclic splines, to capture these dynamic seasonalities in a very flexible way. The BOISA package is interesting too. It's specifically designed for the challenges of weekly data, using methods like locally weighted regression to handle weekly patterns and outliers robustly, going beyond basic harmonic terms.
And Fourier terms, that was mentioned too.
Right, using Fourier terms is another way to think about harmonic regression. It's essentially representing the seasonal pattern as a sum of sine and cosine pairs with different frequencies, harmonics. By choosing how many pairs, often denoted by k, to include, you can make the seasonal shape incredibly flexible from a simple wave, k1, to something very complex that can fit almost any repeating pattern. It's a very common approach in time series forecasting packages.
Wow. So it seems like harmonic regression starts with this elegant, simple idea of using waves.
Mm-hmm.
But it opens up this huge toolbox for analyzing really complex, time-dependent patterns.
It really does. Harmonic regression in its various forms gives us this robust, interpretable way to get at the recurring rhythms in time series data. Using sine and cosine, these fundamental mathematical building blocks, lets us uncover patterns, measure them, track trends alongside them, and even adapt to tricky things like sharp peaks.
And understanding that seasonality is just so critical for analysis and forecasting in, well, almost any field you can think of.
Absolutely fundamental.
So this deep dive has really laid out that foundation, I think. And it's clear there are many paths forward into more advanced techniques and software for anyone wanting to go deeper.
Definitely. It's a field where foundational mathematical ideas continue to provide powerful tools for understanding the real world. The elegance of using these simple waves to model complex cycles is, I think, quite remarkable.
It really is. Which leads me to a final thought for you to ponder. We've seen how sine and cosine waves, these pure mathematical forms, can model repeating patterns in time so effectively. Given that success, what other complex cycles or patterns out there, maybe in nature or technology or even social systems, might we be able to unravel and understand better by applying fundamental mathematical functions in creative ways? Something to think about. Thanks for joining us on The Deep Dive.